Okay, so let's talk about infinite Galois extensions, right? So, uh, usually Galois extensions are finite, right? That's part of the definition. But we're going to be talking about infinite Galois extensions. Okay, so here's a theorem. For any algebraic extension L over K, the following are equivalent. 1. L is a union of finite Galois extensions, Li. 2. L is the splitting field over K of a set of separable polynomials in Kx. 3. The fixed field of the automorphism group of L over K is K. And 4. L is both separable and normal. Remember, separable means every element of L has a separable minimal polynomial over K, and normal means every irreducible polynomial in Kx that has a root in L splits completely over L. So the definition of a Galois extension, and not necessarily a finite Galois extension, it could be an infinite Galois extension. The definition, we call an algebraic extension L over K Galois if it satisfies the conditions above. So this is the condition that I'll think of as like the central condition, and I'll prove that this implies all of the others, and all of the others imply this. Right. So the central condition is that L is a union of finite Galois extensions. Now let's prove that L being a union of finite Galois extensions implies that L is the splitting field of a set of separable polynomials, right? So L is a union of finite Galois extensions, Li. We know that Li is the splitting field of each Li is a splitting field of a separable polynomial Pi. This is because Li is a finite Galois extension. So then L in totality is the splitting field of the collection of these separable polynomials, and that's it. We've proven 2 from 1. Alright, now let's start with 1 and prove 3. So 3 is that the fixed field of the automorphism group L over K is just K. So whenever you want to prove an equality of sets, we prove the 2 different directions. So one direction is obvious. Why is this inclusion obvious? By definition, automorphisms of L over K is the automorphisms of L which fix K, right? So obviously, the set of elements fixed by the set of automorphisms fixing K contains K, right? Okay, so now we just have to show that the set of elements fixed by the automorphisms of L is contained in K as well. So the fixed field is contained in K. So let's pick an element in the fixed field. Let's pick an element that's fixed by all automorphisms of L. By 1, remember 1 says that L is a union of finite extensions. We know that this element that we picked is contained in one of these finite extensions. So alpha is contained in the fixed field of this finite extension. Why? So the automorphisms of this finite extension are just the automorphisms of L restricted to this finite extension. And since alpha is in the fixed field of the automorphisms of L, alpha is also in the fixed field of the automorphisms of Li. Now, the fixed field of the automorphisms of Li is K, because Li over K is finite Galois, and that's one of the definitions of finite Galois. So that means that alpha is in K, and so this is what we've shown, that the fixed field of the automorphisms of L over K is contained in K. So we have both inequalities, so both containments, so that gives us that what we want. The fixed field of the automorphism group is just K. Okay. Now let's prove 1 implies 3. So, no, 1 implies 4. So what is 4? 4 is that L over K is separable and normal. And 1, remember, is that L is a union of finite extensions. So let's prove that it's separable. Separable, remember, means that if you have an element in the field, then there is a separable minimal polynomial for that element, right? So first of all, alpha in L gives you that alpha is in Li using 1. So Li is a finite Galois extension. So alpha has a separable minimal polynomial over K. We're using that Li is a finite Galois extension. So we've shown it. Now L is separable. Okay. So, yeah. Okay. Now normal. We want to prove that L over K is normal. So a normal, remember, means that if you pick a polynomial in Kx with coefficients in the ground field, if it has a root in L, then it splits completely in L over L. Right, so let's pick a polynomial in Kx, an irreducible polynomial that has a root in L. By 1 alpha, this root alpha is in Li for some finite Galois extension. So Px splits completely over Li and thus L. Right. So because Li is finite Galois, Px splits completely over L. In particular, L is normal, so yeah. And Li is normal and contains one of these roots, so Px splits completely in Li. Right. So if it splits completely over Li, which is contained in L, it splits completely over L. Alright, so 1 implies 2, 3, and 4. Now let's show that 2, 3, and 4 each individually imply 1. So suppose that L is a splitting field of a set of separable polynomials Pi. Let Li be the splitting field of Pi. Then Li over K is finite and Galois, and L can be written as a union of these finite Galois extensions, composites of Li's. So why am I writing these composites of Li's here? Because if you just wrote L as a union of Li's, that wouldn't be true, because the union of Li's is not necessarily a field, but the composite of Li's is a field, right? So this is basically just the composite of all of the Li's. Yeah, and this is this gives you L, and each composite is finite Galois. Each finite composite, a composite of finitely many Li's, is finite Galois. All right. Yeah. Now 3 implies 1. 3 is that the fixed field of the automorphism group is K, and then we want to write L as a union of finite Galois groups, right? So suppose that the fixed field is K. We have L is a union of L alpha, where L alpha is the composite of sigma K alpha, where sigma ranges in the automorphisms of L over K, right? So yeah, there are finitely many embeddings of K alpha in L, and this is just the composite of all of them, L alpha, and this is going to be finite, and it's going to be Galois because any automorphism of this is just going to take any automorphism of L applied to L alpha is just going to take L alpha to L alpha. Right. Now finally 4 implies 1. 4 is that L over K is separable and normal. And now we want to show that L is a union of finite extensions, finite Galois extensions. So L is indeed a union of finite Galois extensions, where L alpha, alpha ranges in L. L alpha is a splitting field of P alpha x, minimal polynomial of alpha. So why should L alpha why should L alpha exist, first of all, and why should it be finite Galois, right? So the fact that it's separable, L over K is separable, implies that P alpha X is separable, and then this implies that L alpha over K is finite Galois. But to get that L alpha actually exists inside of L, we need the fact that it's normal. So it's normal means that P alpha X, which has a root alpha in L, splits completely in L. So the splitting field is contained in L. L alpha, which is the splitting field of P alpha, is contained in L. So we use both the properties of separable and normal to conclude that L is a union of finite Galois extensions. Right. So in summary, this is the definition of an infinite Galois extension, or more infinite or just Galois extension, depending on how you want to call this. If you want to say Galois means finite and whatever, but this is the definition you'll use, and there are 4 equivalent properties for this definition, and this is what it means to be an infinite Galois extension.